the sort of optics, and this is setting us up to be able to talk next week about how lenses work, right? Like, remember we said at the very beginning of the class that we're going to look at optics from like a medical point of view, and like if you have, different types of lenses that you prescribe to people, how does that affect like eyesight? So that's where all of this is going. So photons travel in straight lines and can be reflected like little particles. So you can think of a photon as just like, a particle just like any other particle, right? You can think of it as model it like a tennis ball, like bouncing off a surface, right? That's essentially what's happening with reflection. So when light rays strike a flat surface, some of the light is reflected. And the way this works, this is called the law of reflection, is the incident ray, so theta I, so this is the incident ray. So the incoming photon, the incident ray. The angle between the incident ray and the normal, so the normal is just like the dotted line that is perpendicular to the surface, so this is the normal. So the angle of incidence equals the angle of reflection, okay? And this is the reflected ray here. Okay, so this is the incident angle, the angle between the incoming ray and the normal. The reflected, the angle of reflection is the angle between the normal and the reflected ray. And those have to be equal to each other, okay? And that is known as the law of reflection. Okay, and we when light passes from one transparent medium into another, some light is reflected and some light passes right through, right? We saw that over here. So let me just draw it and then we'll look at it again in the demo. So if I have this so this would be the incident angle here, right? Some of the light is gonna reflect, right, at the same angle that it's coming in at. So the incident angle is the same as the reflected angle, right? But some of it is gonna sort of pass through, right? And so let's draw the situation with the demo, right? I've got this clear acrylic block that has a flat surface here, right? So some of the light is getting reflected back that way. But some of it is passing through, right? So you can see that it bends when that happens. And that's why you've noticed this, I'm sure, in lots of different contexts. Like if you have a pencil in a glass of water, the pencil does not, if you look at it from above, it doesn't look like it's straight, right? It looks like it's bent a little. And that's because as the light is passing through the water, it's actually bending. And when you go from air to water or air to acrylic, what happens is the light bends towards the normal. Okay, so here's the normal. I should have drawn it a different color. Here's the normal here in blue, right? That's the normal, right? It's perpendicular to the surface. And this light, the way to think of it is this, like this. If it were passing straight through, what would it look like? It would just look like this. That would be like if it passed straight through without bending. Okay, but what it actually does is it bends this way towards the normal. Okay, so it goes like this, in, and then bends, oh boy, and then bends like this. Okay, so let's look at it. So not this. Okay, here it bends towards normal. Okay, and that's when we're going from air to acrylic. So let's look here. Okay, so you can see that, right? So the light is coming in here, some of it's getting reflected at the surface, and then the part, look at the part in the acrylic. It's bending towards the normal of the surface, right? Okay. So what I want you to do before we keep going with this is see if you can figure out, oh, well, actually, let's talk about this first, sorry. So this is called refraction, and refraction is basically just the bending of the path of light. So bending of light ray. So this is like the photons are actually sort of changing direction, and this happens at the interface between two media. Okay? So why does it bend? The reason it bends is because the speed that the photons are traveling changes when you're going from light to another medium. Okay, so we know that the speed of light in a vacuum is just c, right? It's just that constant that we already looked at, 3 times 10 to the 8 meters per second. But when light travels through some other medium, like water or in this case acrylic, it travels at a slower speed. Okay, and that the ratio between the speed that light travels through some medium and the speed that it travels through air, we define that as the index of refraction, n. Okay, so n is c, which is a constant, divided by v, v being the speed of light in whatever other medium we're talking about. Okay, so this is the speed of light in a vacuum. Okay, and this is the speed of light in some other medium, Okay, so like for example, let's take glass. And acrylic there is pretty close to glass. So what does this 1.5 mean? Like if you had to like explain to somebody like what does 1.5 mean in terms of the speed of light in glass? It's 1.5 times slower than in air, right? So light travels 1.5 times slower in glass than air. Okay, so because air is 1, air is the reference of everything else, right? Air is 1 by definition, right? Because that's like how fast, like if you look at this formula here and you put like n equals c over v, but v is c, then n would be 1, right? So that's what we compare to everything else. Well, air is basically a vacuum, right? There's a very, very small, you can see there's like a tiny difference between the two of them. Water is somewhere between air and glass. Okay, so now what we're going to do is look at something called Snell's law. Snell's law is basically the relationship between the incoming angle of the incoming photon and the refracted angle. Okay, so we've seen this over in the demo. If you've got like this photon coming in, it hits the medium here, right? It's going from low index to a high index. So the light bends towards the normal, bends towards the normal. Okay, so the relationship between the incident angle, and this is called the refracted angle, because now instead of it being reflected, it's being refracted. So this is the refracted angle here. The relationship between those two angles and the respective indices, so the index that the photon is starting out in compared to the index that the photon is ending up in, right? So this is like N1. The photon is starting out in air, and it's going into an index of N2. So that relationship is this. So if you take N1 of the index that the photon starts out in, you multiply it by sine of the incident angle, it equals N2 times sine of the refracted angle. Okay, and this is referred to as Snell's law. So what I would like you to try is to derive this like I did on the page before with the law of reflection. Okay, starting out with like all of these assumptions. So the same assumption applies regarding the energy of the photons, right? The energy of photons is conserved, just as it was in the case of reflection. Okay, so we know that the initial energy of the photon here in the air is going to equal the final energy of the photon here when it's in the glass. Okay. However, this is different, right? The wave speed, we now know the wave speed changes, right? And we know that wave speed is governed by this relationship. Okay. What about the y component of the momentum? The y component of the momentum definitely changes. How would you describe that change, just looking at this diagram? Remember we said in this situation up here, back here, we said that the momentum changes from, the y component of the momentum changes from negative to positive. What happens here in this picture? Oops, down here. If I had to like draw, does it go from negative to positive? No. It becomes more negative, right? So the y component of the momentum changes due to the force at the interface. That change, so the y component becomes more negative, which is interesting. Okay, the x component is still conserved, right, for the reasons that we just talked, for the same reasons. There's nothing that changes the momentum of the photon in the x direction. Okay, and those are all the facts. So those, like, you know those four things. Okay, so using those four things, try to derive this. Okay, and again, like, think about it for a couple minutes yourself, and then turn to the people around you. Okay, so let's start going over this. So we're going to start off in the same spot that we did with the previous exercise, right? By saying what we know to be true about the x component of the momentum before and after it goes into the water, or glass in this case. Okay, so we know that the x component of the momentum initially equals the x component of the momentum finally, right? So the first two steps are basically the same as they were when we were looking at reflection. Okay, and then we can say that we know that the momentum is just equal to the energy over the velocity, right? So this is the incident angle equals the energy final over the velocity final times the sine of the refracted angle now. Okay, and the energy initial is energy is still conserved. So energy initial is equal to energy final, right? So these you can cancel out, right? But the velocity changes, right? And I know that the velocity is just c over the index, right? So I could write here n1 being the index for the air, so the thing that it's starting out, divided by c times the sine of the incident angle equals n2, so the index of the thing that it's like refracting into, divided by c times sine of the refracted. Okay, and c is a constant on both sides, and so you end up with Snell's law. Okay, how many people were able to actually get that? Yeah? Okay, great, nice. Okay, so I just wanted to show you, so I've already sort of demonstrated how when you're going from a low index to a high index, so like when you're going from air to acrylic, the refracted beam bends towards the normal. When you're going from a high index, so this is like high N here, you know, when you're going from water to a low N to air, the opposite happens, right? So if this is the incident ray, and imagine, like I always think about like, oh, what would it look like if it went straight through? It would go like this, right? Just continue this. My tablet is not completely calibrated, but it would continue through straight from the incident ray, right? That would be what it would look like if it would go straight through. So you can see that it's bending away from the normal when you go from a high index to a low index. So exactly the opposite, right? So I can demonstrate that up here. Where is the button? Oh, here. Okay, so you can see like from the acrylic to the air, it's bending, right? So you can see imagine what would happen if it went straight. It would just be like that, but it's bending away from the normal in that situation. Does that make sense? Okay, so hold on. Let me just clip this down because I want to show you one other thing, which is, okay. So let me just change. So here you can see that there is some reflected light here, right? And then there's this light here which is refracted. Okay? Let me show you what happens if I increase the incident angle. Okay, so remember what the incident angle is. The incident angle is the angle between the incident ray and the normal, right? So it's this angle here. Okay? So if I change that angle and I increase it, I would have to move the laser this way. There's this like magical point that is called the critical angle, where the light completely internally reflects. Okay, so why don't you guys sing out when you think that I've got to that critical angle? Okay, so let me start here. I'm going to start with a small angle, right? Okay, and I'm going to increase it. Tell me when you think it's happening. Right, like right there, right? Just and what's sort of happening like to the refracted? Like if you had to say what angle the refracted light is going at, can you see like, okay, now I don't quite have it. Oh, now I kind of do. Like what's happening to that refracted light? Pardon? Yeah, it's traveling along the surface. It's exactly at a right angle, right? Do you see that? Like at that critical angle, the refracted angle is 90 degrees. Is everyone convinced by that? Right, so here I don't quite have it, now I have it. Okay, so that point at the critical angle, so when the incident angle is what we call the critical angle, you have total internal reflection. So like the refracted, it's like the refracted ray is like traveling along the surface, right? i.e. at 90 degrees to the normal. Okay, so let's just look at some of the math associated with that. Because total internal reflection is a really, really important concept in optics. Like there's all sorts of things, like it's how fiber optic cables work, for example. Okay, so I'll show you like some demonstrations. Like this is a demonstration of a fiber optic cable. I'll show you a couple more in a second. Let's just kind of quickly go over what the math looks like. Oh, I left my pen here. So you can express Snell's law. You could reorganize Snell's law just like this. You could say sine theta 1 incidence. So sine of the theta of the incident ray over the sine of theta of the refracted ray equals n2 over n1. Right? Is that right? I just rearranged this. Okay? So when we are at the critical angle, so when the incident angle equals what we call the critical angle, this refracted angle is at 90 degrees. Okay, it's sort of like the light is traveling kind of like along the surface of so if this is the water, so here's the water, and here's the air, and I'm coming in at some incident angle, right? And let's just say that incident angle is equal to the critical angle. What that means is that the refracted ray is like this, right? So this is the refracted ray. So that means that that's 90 degrees to the normal. Okay, so that's a special point where all of the light is totally internally reflecting. Okay, so when that is 90 degrees, what is sine of 90? The sine of 90 is 1. So what this formula, so you have this sine of, now I'm going to call that the critical angle, because that's the angle I'm talking about, over sine of 90, which is just 1, right, equals n2 over n1. Okay, and if I were to like ask you to calculate the critical angle, what would you do? Mathematically, what would you do? You just take the inverse sine of that, right? So the critical angle would just be the inverse sine of the ratio of n2 over n1. So because of the sine function, remember the sine function oscillates back and forth and it can never exceed 1. What does that mean about n2 compared to n1? Like when can you, like what is the situation for which you to have total internal reflection, like mathematically? So this fraction must be lower, must be smaller than 1. Does that make sense mathematically? Like it doesn't, the sine function wouldn't work if that wasn't the case, right? Sine can't exceed 1, right? So what does that mean about n2 versus n1? Right, exactly. So that means that, therefore, n2 has to be smaller than n1. Okay? So you can only have total internal reflection when you're going from a high index to a low index. So like when I'm going from the acrylic to the air, I can't do it when I'm going from air to acrylic. It just doesn't, the math doesn't work out. Does that make sense? Does anyone have any questions about that? Okay, so, oh yeah, so should we do the demos, the other demos having to do with total internal reflection? And then we'll do a am I getting it and take a break. Okay, okay, so the fiber optic cable, this is a fiber optic cable, and I've got a laser here. And basically how fiber optics work is there's total internal reflection happening like many times along the length of the cable. So like if this is the cable here, and I come in with some ray here, like maybe I'm coming in at an angle, it's going to like completely, totally internally reflect, basically bounce back and forth along the cable. Okay, and you can see that regardless of how I bend it, it's going to come out the other end. I don't know if that's convincing, right? So you can see the cable is bent in my hand, right? Here's the cable, it's bent in my hand. I put the laser in at one end, and the light comes out, right? So that's how fiber optics work. Like it's the photons are totally internally reflecting inside the cable. That's also how this thing works, right? Regardless of how I bend these fibers, the light, which is in the middle here, it can still be seen at the terminus of the cable. Okay. There's also this demo. Oh, there's this basically demonstrates the same thing. So this is a piece of acrylic, and it's obviously twisted. And you can see that if I put the laser in here, right, the light totally internally reflects inside. Right, you can see the light all through the cable. Okay, and then finally, we've got this demo here, which, so this is a bottle of water. It's got a hole here on this side, and the hole is lined up with a laser here. So we're going to turn the laser on, and this rubber stopper is like preventing the water, sort of like a vacuum, right? Like it's preventing the water from flowing out. But as soon as I remove this rubber stopper, light is going to pour out of the hole. Okay, so what would you expect to happen? We've got light that's shining in here, and then I'm going to have a bucket right here, and the light is going to cascade into the water is going to cascade into the bucket. And what would you expect to be able to see with the light if it's totally internally reflecting, for example? Yeah, it'll follow the path of the light. Okay, so should you do that?
Mm-hmm. Yeah, so just hold it like that.
Okay.
Okay, so here we go. 3, 2, 1.
So that's pretty amazing, right? How far should we go? Are you convinced? Yeah, so you can see that that's what's happening inside the water. The light is totally internally reflecting and is therefore following the path of the water stream. Okay, so should we cap it off? So that's pretty weird, right? Yeah, so this is just a trick that the demo people love because there's like actually little LEDs in the bottom of the, so just to, I don't know, to amuse you mostly. So I mean this is obviously like not part of the physics, right? This is just a trick. It's what's happening here that, okay. How is it a trick? Oh yeah, no, me too. No, it's okay. So, great, thank you.
Sure.
Okay, so any questions about anything to do with total internal reflection or refraction or anything that we've done so far? Yeah? Oh, what's special about the bottle? Well, okay, so there's nothing special about the bottle. The sort of interesting physics is here at the interface between the water stream and the air, right? So remember we said that total internal reflection can only happen when you're going from a high index to a low index. So basically what we're doing is we're sort of shining the light through the high index medium, right? And then so it's flowing like through the water is flowing through the air into the bucket, right? At the interface between the water and the air, because that's going from high to low, the light is basically reflecting back and forth in the stream of water because of the light-air interface. So that's what allows that phenomenon to occur, is total internal reflection. There's nothing special. I mean, the only special thing is like this cork is holding the water in, right? But that's the physics of that is slightly different. Yeah, any other questions? No? Okay, so you have all of the tools that you need to be able to answer these questions, these am I getting it questions. It's 7:30, so this is probably a good time to take a break. The second half of the class is completely different. So this is sort of like, we've now covered like all of the electromagnetic spectrum part and the light, looking at light as an example of an electromagnetic wave. And so now the second half of the class, we're going to talk about magnetic resonance imaging. So we're going to completely shift gears. So try these questions and take a break. So why don't we come back together at 7:50 to give you like a little bit of time to both take a break and try the questions. And then we'll pick up with these questions at 7:50. Okay? Great. Okay, so let's pick it up again. Somebody asked a really good question during the break, and I just wanted to make sure that this is totally clear to you. N1 and N2, so N1 is like the medium that you start in, and N2 is where you end up, right? So like this picture, I think some of you thought that N1 is always air, and N2 is always something other than air. That's not true. Like, see here in this picture, it's going from N1 to N2, where it's going from air to water. Here, it's going from water to air, right? So like in this case, N1 is water. So the 1 and 2 refers to like where you start and where you finish, not like any specific medium. Okay, so I just wanted to make sure that was really clear. So, okay, so let's go through these. So you've got a ray of light in air enters a piece of glass, as shown. Which path shown in the figure could the actual ray path be? So here, we're going from, so this is N1. N1 is air. N2 is glass, right? So what would you say about the velocity of the photon in N1 versus N2? Is the velocity higher or lower? Higher. Okay, so velocity here is high. Velocity here is low. Okay, and this is like N1 is lower than N2, right? So N2 would be like 1.5, right, in index. N1 would be 1. Okay, so which of those rays, A, B, C, D, or E, do you think that it makes sense? So I'm going from a low index to a high index. So which way is the ray going to bend? Towards the normal or away from the normal? Towards the normal, right? So which path makes most sense? C. Okay, so like this would be, path D would be like if it didn't bend at all, right? It's going straight through. You can see like path 3, if this is the normal here, like B, like basically B is the path B is sort of the normal. It's perpendicular to the surface. So you can see that compared to going straight through, C is bending towards the normal. Okay, so C is right. So next one, the figure at right shows a light ray traveling in a medium with index N1 and and reaching an interface with a medium of N2. On the diagram, label the angles N1 and N2 as defined by Snell's law, then answer the following questions. Okay, so the angle theta 2 is what? 0, between 0 and 90, or 90? In this little picture, 90, right? This is clearly 90, so C. Okay, what must be true about the indices of refraction, therefore, for you to have this kind of a situation where you're going here, N1 is clearly bigger than N2? right? Which is choice C, right? I'm going from, like, say, water to air, right? Remember we said that for the mathematical reason that I explained, in order for you to have total internal reflection, which is like, there's no refraction out here. All of the ray is getting reflected kind of along the surface of the medium. You have to be going from a high index to a low index. Otherwise, you can't have total internal reflection. Okay, last one. What would happen to the outgoing refracted ray if the angle here, if I increased this angle? So this is theta 1, right? And this is theta 2, which we're saying is 90 degrees in the case of total internal reflection. So if I increase, like, this angle, so, like, and I showed this to you, if I go beyond the critical angle, so if, like, the angle exceeds the critical angle, then what happens? Which of these choices should I pick? C, right? There's no outgoing refracted ray. So, like, the critical angle is the angle at which total internal reflection occurs. Any angle beyond that, you're also going to have total internal reflection, right? So, like, when you go past that point, you still don't have any refracted light. It's still totally internally reflecting, okay? And like we said, that's, like, how fiber optic cables work. Okay, so any questions about anything to do with the optics?